It's a pleasure to be here, and I must say that I appreciate the time of you for being here and working with you together here, and I hope to meet you soon again. And I'm happy for the collaboration that we have had and have. It's like more than 2 years, or a little around 2 years, that we are not having frontal conferences, and it's still strange for me. But if somebody wants, it's okay for me to turn on the camera. It's up to you, but you can stay like as a black square, or you can put camera, whatever you prefer. It's all the same, but it's not easier for me to see faces, but it's up to you. The aim for this book, the title is Remote Sensing and Machine Learning. Hi, Manuel. It's remote sensing and machine learning in agriculture. And the question is like, can we assess what we do not see? And what the idea of the main aim of what I'm talking about will be to have some little background about remote sensing and its relation to agriculture, and see the potential for artificial intelligence, machine learning, deep learning. It's a lot of big words, but to show the potential, show a little bit of some of the work that we have done, not in great details, but just to show, but mainly focus not on the analysis concept, but more to focus on the agricultural concept, on the remote sensing concept, and the potential that there is still for deep learning, machine learning, etc. This is the concept and the scope of this talk. That's it. There is a link for our lab over here. If somebody is interested, they can contact us. And it's just nice to show that the date, you can switch it from side to side this day. 2nd, 22, 2022, you can read it from both sides. It happens once in a while. Forgot the name of it. So let's start. First of all, okay. First of all, this is our lab. We need to change things. We have already here, we have also Maitreya. He's a visiting PhD student from India. We are happy to work with him. We'll show, I think we'll talk about some work that he's doing later. This is us. We're working on from imagery from space. This is Venus imagery from a paper we published recently with Professor Carnielli and Dr. Salvoldi here. And we talked about the advantages of a red edge inflection point index. I guess many people know NDVI that we see here, but there are also other indices that they might have advantage. And this is one of them. We're working on from UAVs, hyperspectral UAV, and hyperspectral indoors also. We're developing now also a cart for data collection in the field, and a few other things as well. So this is us in general. Before we start, the acknowledgements for many people that some of the collaborative work is presented with them. It's students, the agricultural guides, professors, researchers from Israel and other places. So this is to acknowledge their collaboration with us. This is to start, and the motivation is, in general, the population of the globe is growing. The good news is that the rate growth is decreasing, so there is some positive angle to it, and most of us like to eat. And I think everybody knows chickpea, good food. Everybody knows sesame. You can make many things from it. In Israel, around Israel, if you combine both of them together, you get what's known as hummus. And most people prefer to eat it with wheat, with pita bread. So the motivation is food. Now today we'll talk, I think, a little bit about each of these crops. We'll talk also a few words about corn as well. But this is from studies that we have done or doing now. But in general, for what we are doing and what we saw about the population growth, it's nice, but who knows what is going to happen in the future. For that, there is a person from Lebanon. His name is Nassim Nicholas Taleb. Most of his life, I think, he lives in the United States. he was doing statistics for economics, for investments. He wrote few books. One of them is A Black Swan. For him, a black swan is the name of an event. Like if you live your whole life and saw only white swans, the first day you see a black swan, it's a surprise. You don't expect it. But this is not with a huge impact. The idea is that it's a black swan event for Nassim Taleb. What he defined it was an unpredictable outlier that has an extreme impact. And when you look back, you think I could have guessed this one. And this is it. I guess all of us has an example in our minds now. And I guess in most cases it's related to this one, to COVID. And there were papers about it. So in retrospective, it was predictable and could have been, I'm not sure if avoided, but could have been better prepared or something like that. But it's easy to say post. The event like this is the invention of penicillin. It was by mistake. Lives of millions were saved. Another event, less happy, is the Dust Bowl in the United States. Something like 90 years back, people were starving in the United States. And there are people alive that still remember this. And some people are saying that putting like the invention of personal computers and internet, IoT, and the computing capabilities is something like that for agriculture. It's like a game changer. Many people think like that. In many parts of our life, the power of the machine is impacting, and in agriculture, I think, and many others, that the potential is not fulfilled yet, and is far from being fulfilled yet. In order for people to eat, if the population is growing, you can cultivate more land. But on the other hand, the area on the globe is limited. Therefore, most people looking at the way to feed the growing population as improving the yield production per area unit for the 1 square meter to have more food out of it. And there are two main ways to get there. One way is to improve agronomical practices, to better fertilize, to better irrigate, to know when to seed, to know how to use pesticides, and learn how to do all the agronomical activities in a more efficient way and use it for the right time to do them, etc. This is one part of it. And in modern agriculture or digital agriculture, there are many ways. It is known as precision agriculture. And it looks at bigger parts like commercial fields in case of field crops or orchards. If there are all kinds of greenhouse crops, it can be used over there. Precision agriculture is also related for animals. But in our case, let's say it is mostly commercial fields, and the scale is big. So in most cases, use satellites, and the data collection is in higher level than close range. We'll go deeper to precision agriculture later. And the other way to improve yield is by breeding, by selecting for genotypes that can provide better yield, that are more resistant to certain disease, that are more resistant to drought. They have longer roots to go deeper in the ground to get water, etc. They can grow faster to avoid the effect of weeds or to reduce the effect of weeds, and more and more and more. So the combination of agronomical practices and breeding, this is what increasing yield in most of the crops, something like 1 or 2% per year for many years now. There have been agricultural revolution, green revolution, etc. It's a combination of genetics and that. And if we look at breeding, both of them, for precision agriculture and breeding, if you collect data from satellites, from UAVs, you're doing like what's known as high throughput phenotyping, like you collect a lot of data in words. If we look at this plot, it's something like, it's not big, it's something like 10 dunams, it's something like 2 hectares, something like that, or even 1 hectare, something like 1 hectare. And in this hectare, there's more than 1,000 plots. To do it manually is crazy. But if we use the UAV, if we calibrate the models, we can assess the height of the plant, the other traits of the plant, and learn about it. This is the use of remote sensing and in breeding and phenotyping projects. To look at it in another way, the high throughput phenotyping, if we look at commercial fields, there is the crop itself, there is also the soil, and there are people that need to make a decision. All data can be collected in many ways, but in the bottom line, it's data that is running from a combination of many sources to the tractor to do some activity in the field and go back and decide again. And this is a management strategy that we'll talk soon about. And breeding is selecting for new cultivars, as we said. And there is also some kind of a cycle. You collect the data, you have raw data, you analyze it, you get decisions, and then you can do some kind of control as in the field, or you can have decisions for the next breeding project to decide how to operate beta. And in genetics, it's not enough. We have the environment, we have a genotype, and in agriculture, we also have management, persons that decides if to irrigate or not irrigate, if to fertilize or not fertilize. And management and environment can be combined somehow, but in general, there are effects of the environment. If the temperature is growing, there is going to be effect. If in average the temperature is growing or the rains are more or less scattered, it will have some effect on the crops. So the combination of genotype, environment, and management, this is the important part for people that are doing breeding. And you want to breed to try and minimize the effects of the environment, or even use or find crops that are happier or can produce more under growing temperatures or more viable conditions, etc. It's not only commercial fields and breedings, but there is also indoors research. There is the urban farming that is the emerging concept, and many people like it in the past few years, and it's going to be probably huge. And on the other hand, I guess it will be very complicated to grow amounts of corn or wheat or soy or chickpea or potatoes in urban farming to feed the world. I think it will be very challenging, but there are many crops that can be grown commercially like that, and it looks that it's going this way. For our lab, we are involved in a project that's called ISERF, Israel-Singapore Urban Farming, and we are working in Singapore. We're starting this project these days, and it's a multidisciplinary team that includes engineers and plant scientists and AI people, like artificial intelligence people, and me as remote sensing person. So this is what we are doing. We're doing a combination of all of this. We are going to have with Professor Menachem Mushilion from here, with Professor Matan Gavish from computer science, and with Kiwei from NTU Singapore. And the idea is to have sensors in the soil next to each of the pots, and to have cameras above them. There is a table with many pots and with cameras running back and forth above it, and sensors in the soil and next to the plants. And based on that, this is how it's going to look. And the company that will build it is Lemnatech, will build all the remote sensing part is Lemnatech. And this will allow us to have huge amounts of data. And now it needs to make sense as we have the data storage, everything is collected. And to be honest, for this project, we are looking for a highly motivated and qualified postdoc that has experience with Lemnatech devices and techniques and software. To do phenotyping, there are many ways. PSI is another company, it's not Lemnatech, they do similar stuff. They are in Czech Republic. Lemnatech is in Germany, they do indoors and outdoors. Here, pots are moving from place to place and moving from chamber to chamber. This is in their headquarters in Brno, Czech Republic. And pots are measured with the highest perspectral, thermal, RGB, fluorescence, and tons of data are collected, but the plant itself is not staying in the same condition. The conditions are changing, and if a plant is moving, it can affect its performance. Here there is a bridge with many sensors that is moving back and forth, and you can collect collect tons of data. In Zurich, they've built like a spider running over there, but I think in Zurich they've neglected this and moved to UAVs. There is like all kind of phenomobiles. You have a tractor with a bunch of sensors. You can have some kind of a robot with this is a ladybug from Australia, and you can have something less sophisticated, but still you can collect very good data with that. And of course UAVs, which is very fashionable in the current few years now. So there are many ways to collect data in relatively close range. And going specific back to precision agriculture, there is a ICPA, ISPA. It's the group of people, the International Society of Precision Agriculture. And a few years back, they have written this, and many scholars have discussed every word here. And in general, it talks about the right manner. It's a strategy to implement in agriculture and to use the right treatment in the right place, in the right time, and in the right manner. And the idea is to improve productivity and quality and profitability. Every word here counts. And if you want, you can read it, you can check it on the site. And usually when you read a paragraph like this, what you think about is everything is computerized. You have UAVs, you have robots, you have trucks and combines that are talking to each other. And the farmer sits at home in his underwear with coffee and looking at the screen, and everything is moving automatically from place to place. My guess that this is only partly true, because if there is no person that understands plants in the field, or soil, or disease, and other stuff in the field, it will not be perfect. And it's also important to remember that not only high-tech is precision agriculture. If you look here, this is somewhere from East Europe. People are lying behind the tractor is driving, and people are picking cucumbers and putting them on the moving platform ahead, and they are all dropped to a carton box, and the tractor is driving slowly and people are picking. The other way would be to drag the box drag a box and walk and destroy the entire field. This way you can pick and come back in 2 or 3 weeks again and again. So productivity is improved, efficiency is improved. So this is also precision agriculture. So I think it's important to remember that as well. And as mentioned a minute ago, there is a lot of information. You can have all kinds of soil sensor, moisture. You can have UAVs, you can have satellites, you can have all kinds of handheld devices. You can combine together with genetics. You have some data from the tractors that is site-specific, because tractors has high-quality GPS. All the data is sitting here or in the cloud. You can have a map, and now after all the data is analyzed, the tractor can go to the field and fertilize in viable rates throughout the field, or use pesticides in viable rates. In Israel, people are already using pesticides by UAVs. Somebody is doing a map. With one UAV, you do a map of the weeds, and the bigger UAV with a tank can go and specifically spray where is needed. Not everywhere, but people are doing it, mainly in orchards. It works fine. It looks like it saves time and money. So this is a precision agriculture concept. It's based on a lot of analysis and a lot of models and a lot of data, and it has to be done the right way to be useful. And I'm sure that not every farmer can do it, or very little farmers can do it. But it's something that is probably in the future for maybe bigger companies or groups of people or farmers. For us, if we look about data analysis, what we have between our chins and forehead is a very good system. We can, for fractions of a second, we can look and we know what we see, and we can classify it, and we know exactly what it is in very fast. There are all kinds of methods that I'm sure you all know, and that we try and teach computers to do it in all kinds of success rates. The main question is about our system. Can our system be operating in complete darkness? And I'm sure that everybody knows that the answer is no. And the reason is because our sensors are not sensitive to that. We're not sensitive to UV, we're not sensitive to infrared, we don't. So if we could increase the usable spectral range, we could have done that. And if we can, and we cannot be at all places at one time. If we want to look at a field, to scan a field for looking for damage by a certain insect, or to look for signs for early drought or fertilizer deficiency. So we cannot be in the entire field at once. And this is where remote sensings come to the picture. You can cover the entire field. And examples for research that we were part in, first of all, the paper that Arun concluded in his visit here, talking about combining UAV and ground level with satellites and airborne to play with different types, like a multimodal analysis with different types of sensors, part of them imagery, some of them hyperspectral, some of them multispectral, also point spectra, and to get the correct labels and improve them. And he developed methods to do so. A project done with people from Wageningen, working about GAN, playing with the ability to detect early drought. It's not a crop, it's Arabidopsis, but it's indoors. Also interesting. And a paper in progress that is based on point measurement, comparison between several analysis methods, building all kind of feature selection, and combining spectral data with vegetation indices and without, to develop new methods to estimate pigments content in leaves. In this case, it was sesame leaves. So this is in preparation. We're about to submit this one. So if we have a research question, we need to find the right tool for it. We need to be, it must be right on the spatial way. It must be fitting, and it must be fitting on spectral level as well as temporal. There are many options, from leaf measurements to satellite. You can have spatial measurement, spatial pixel that is 1 millimeter or 1 kilometer, and there are many things, but you can't always get what you want. It still takes time. It will be some time before we can get all the globe covered with hyperspectral imagery in 1 meter or something like that. But the good news is that it's getting better and better. And just a word or two about spectral resolution. Usually in our phones, we have RGB, red, green, blue, 3 points, but we don't know what the slope between them looks like. If we have multispectral, we have a little bit more. Some people call also 3 bands multispectral. The definitions are somehow vague. And this is multispectral. We still don't know what goes on in between. If we go for hyperspectral, the blue line, we can see that it's not a line, but there are many, many, many dots. So there are many bands, no 3, 4, 5, usually hundreds, and they're very close to each other. And together they create the line. And we see that it's much more sensitive than the lines that we've seen before. And there is also here for plants, this little blip, it's related to the atmosphere absorption of oxygen. And this can allow us to see the fluorescence of plants. If there is too much radiation coming in, the plant is throwing some of it out as fluorescence to avoid extra heating. And so this is for spectral resolutions, but there's also temporal and spatial resolutions that should be considered. We talked a lot about remote sensing, but some people will call remote sensing only if you work with satellite or high altitude, high flying aircraft. Some people will call remote sensing if you work with a microscope. So it's depending which discipline you come from. The idea, the 2 big groups on remote sensing is active and passive. If you are active, it means that you like a LiDAR, or you throw some signal and collect it. And if you're passive, you use the sun or other sources. What we are talking about is mainly passive, spectral, or thermal analysis. This is what we are doing usually. And if we look at the electromagnetic spectrum, from the shorter wavelengths to the longer one, we are in the visible somewhere here, and we can do a little bit more. If we are based on the sun, on the x-axis, we can see wavelengths from the shorter to the longer. And on the y-axis, we can see how much is emitted energy. And we can see that most of it is in the visible part, and this is Therefore, there is no surprise that the plants are active this part. They absorb energy for photosynthesis, and our eyes are used for that. And many of the animals are using that. Also, some insects are using UV, and some other animals are using longer wavelengths in the thermal. But still, we were affected by the sun very much. But what the sun is emitting is not what we get on Earth. The yellow part is what is filtered by the atmosphere, and what we can see is only the orange one. And here, if you look carefully, you see the absorption of oxygen, which is around 760. So the atmosphere is almost oblique. You cannot see through, and therefore it can be that some signal from fluorescence is possible to be detected. And Europeans and others are working on it hard, and there's probably going to be launching a satellite for that soon. But there are many studies about sun-induced fluorescence with plants, and most of them are around this absorption because the atmosphere is blocking most of the natural radiation, so you can see what the plant is fluorescing. Things had spectral signatures. If we look about water, it's very little. If we talk about soil, there is a one feature, and if we see vegetation, there is a different feature. There are different features. And x-axis is wavelengths, y is relative reflectance. In a minute, we'll say why it's relative and how to work with that. And we look at the visible, the reflectance is very low relative to other parts because most of the radiation is absorbed for photosynthesis by the plant. Here, the red edge region is the steep slope going upwards towards the near infrared that is mainly affected by biomass and structure of the canopy. And if you have more layers of more canopy, you'll have more and more, you have higher reflectance in the near. And in the sphere, this area is mainly affected by water. And but it's not strict. Some biomass affects here and water affects there, but this is in general the main effects. It's important to remember that this line is a pool of all traits, because if the plant has not enough water, there is going to be an effect on the pigments. There is also going to be effect on the leaf, because if the plant without water for a few days, the leaves might be dropping. So the pressure in the leaf, like the turgor, the water potential will be dropping. And then the infrared part, the near infrared that is related to biomass structure can be changing as well. So it's important to look, my thought is to look at the entire range, as if we're doing it hyperspectrally, to look at the entire range and see what can be done. Because in some cases there are specific absorptions that are specific for certain materials, but looking at more bands might be more efficient, not in all cases. But to do that, we need to do it the right way. I think this is the most complicated slide in the entire talk, so I'll start on the left. What we see here on the x-axis is wavelengths, on the y is reflectance. We see it's a sunny day. The red line is the upwelling radiation, meaning that the radiation that is reflected from the soil or vegetation up and is measured like by a sensor that facing down. And the black line here is the downwelling radiation measured by a sensor facing up that measured directly the sun. So it is this shape is similar to what we saw before the sun is emitting. And this one is similar to a plant, but it's not corrected yet. So this is a sunny day, a very similar target alone. And this is a cloudy day. You see the intensities are much smaller, and there is some variability because of changes in the atmospheric transparency due to clouds. But if we take the red and divide by the black, or if we take the blue and divide by the black, we get very similar results. And this is the idea, because if I look at my hand now, when the room is lit, I'll take a picture, the value in the pixel will be 150. But if I will look at, I'll turn off the lights and close the windows and everything will be dark, I'll take a picture, the value will be 4. So it's the same hand. The target have not changed, but only the environment. Therefore, we must do like referencing, and this is the idea to divide by the sun, that is, but by the radiation available by the sun. And this way we can get a good result here. All the numbers here are because of the integration time and because of the exact field of view, if it's 25 degrees or 180 or other stuff to end the exposure time to correct for that. And this is how we get a nice spectral signature. Oh, this is it. Yes. And if we look at chlorophyll, the blue means that there is a lot of chlorophyll. Red, it means that there is almost no chlorophyll. So plants with a lot of chlorophyll absorb, and plants with less chlorophyll reflects more. So the ratio is negative. We can see also on the red edge that there is a blue shift. If it's not accurate exactly how it's presented here, but in general, at least in the lower part of the red edge, there is a blue shift because plant is reflecting more and the chlorophyll absorption is covered. So this is much about like background, and we'll start going to plants. This is chickpea. If we talk about chickpea, the global production, the main country is India. I think it's called China or something. This is what I remember. And if we look, this is area of production, and here we look at yield. And India is not in the first place, but in the first place, there is a little country here, Israel, in the yellow part. And the reason for this difference is mainly due to irrigation. It's not because of the irrigation here, it's not enough to irrigate, but it is needed to be irrigated. In flooding, it's lesser quality because of danger of diseases, and the irrigation is not used at the exact, it's the best time for the plant. And if we're talking about farmers that are growing in Israel, the cycle is seeds. In winter, plants have been sown like a month ago, give or take, and they are sprouting and growing, and now they are somewhere around this size. And soon the rains in Israel are going to be finished. No more rain. And then the farmer needs to decide when to irrigate. If you irrigate too early, it means that you'll start to have a very vegetative plant, a lot of leaves, and almost no pods and no seeds. And then the plant will collapse, and it will be very complicated to harvest. If you wait too long, and then the plants might get, if you wait too long before irrigating, the plant might get to stress, a terminal stress, will have 2 or 3 layers of pods, and then stop growing, and that's it. So there is a sweet spot, and you need to know exactly when to irrigate. This is a big question. And the way to do it, usually what people are doing, at least in Israel, is one thing is to ask their neighbors if they have irrigated or not. This is one common practice. The other practice is to use a pressure bomb. It's you pick a leaf, you put it in a cabinet that is sealed only for one opening, and the petiole is going out, and then you put pressure by gas to this chamber, and the minute you see some water coming out of the petiole cut, you know that this is a water potential, and you see the pressure, and you can estimate by that the water status of the plant. Usually people in Israel are irrigated, there are numbers for that. So this is a motivation for the study about the chickpea that we'll show now. We've used for that Venus, which is a lot of help for Manuel. And Venus is a unique Israeli French satellite. It has 11 bands, 2 days revisit time, 5 megapixel, more than 100 sites worldwide. In Israel, 27, more than quarter, or like about quarter, and they cover most of Israel, and it takes less than 3 minutes. These are advantages. The disadvantages that it's only 100 sites and not globally, and not without a global cover, which is Sentinel can do, but there are many advantages, and Venus was aimed to be as a research satellite. So this is Venus, and we used it, and it was great. We'll talk in a second. We also did some data collection on the ground. This is Gabriel, Roy, and Prost working with 2 spectrometers. One is here, facing the white panel, and this is measuring the sun. And the other one is on Roy's back, and he's working with it in the field and collecting reflectance from the plant. We put them together, we can get the corrected reflectance. And this is how it looked. Oops, it's in Hebrew, I'm sorry. It should say here chickpea. And we see on the x-axis wavelengths, on the y-axis reflectance. The colors, it's 100%. It means that this is the best irrigation that the farmer could give. It is based on transpiration and evaporation, on more, not transpiration, but more about evaporation. It's called the Penman-Montis equation, and based on that, it was decided what is the best irrigation to provide. And there were other 4 treatments, 2 with deficit irrigation and 2 with exceeded irrigation, too much. This is the day before starting to implement the differential irrigation. And we can see the vertical lines. These are water vapor in the atmosphere. So we couldn't correct them completely, but we could collect twice as data as if you work with 1 spectrometer, because if you work with 1 spectrometer, you do white reference, then it takes a while, and then you take a measurement. And if it's partly cloudy and not exactly clear, you need to do it again and again, like it's 50-50. 50% of your time you're referencing and 50% of your time you're measuring. If you work with 2 spectrometers, it's almost most of your time you collect data. So you collect much, much more. And this is how we work now. And this is 3 weeks later. We can see the effect of irrigation in the near infrared on the biomass. And we also see that this was the atmosphere was much clearer on that day. And we can see that the colors are sorted by chronologically from yellow to red, but the other way around. Less irrigation, smaller vegetation, smaller reflectance. Red, high irrigation, high vegetation, high reflectance. This is how it works here. Another 3 weeks, we see that this part is the same. We see that the day was a bit more clouded than before, and we can see that there is also chronological separation in the visible part and in the SWIR parts. And both of them, they go just the other way. So if you have less water, this is how it looked. This is not from the first season, this is from the second season. So you see also the gray treatment here, that is no water, 0 water at all. But you see how the field look like from a UV. This is from the first season. And if we throw also thermal on it, you can just see these 2 lines are these 2 plots. We can see that lighter colors, it means higher temperature, darker colors, lower temperature. And you see that you can see it by temperature and spectrally as well. If we worked on ground level, LAI, leaf area index, from 3 sites, it's 1, 2, 3, 4, 5, 6 sites together. Together it's 6 sites. We can see all of them are linear, and you can see this is done by PLSR. Roy and Omer are both of them PhD students with us. Roy did his master's on chickpea and now is working on wheat, and Omer is now doing his PhD on chickpea and pushing on with this data. So we have 6 sites, 4 of them in farms and 2 of them in commercial fields with these treatments, and all of them are linear. The same for water potentials that we talked about, you measure it. So water LAI, it's like leaf area index, it's something that you can actually, when you look at the plant, you can assess how many layers of leaves you have or something like that. But if water potential is something that you must measure and you don't see, and this is the unique part, but it's an ongoing treatment. So we might be seeing the effect of the irrigation on the development of the plant, like on the LAI. But here we do correlation between water potential and dry matter and LAI, and we see that it's low. The spectral relation to water potential is about 60, a little bit more. The validation is about 60, and here you see if we combine both of them, dry matter and LAI, also they are highly correlated. Let's say it's like 0.4, so still we have 20 that is not explained by them. So we're going back to the concept that spectral reflectance is affected by all traits together, and sometimes it's hard to separate. Another thing that was done was yield assessment. This is only in 2 years in Gilat, in 1 site, and this was done by Roy. We can see here on the left, the 50%, 75, you see the yield related to treatments. You see that at a certain point, more water will not give you a better yield. And the next year, we have also the 0 treatment, and we can see that the yields are much lesser. 3.5, and here we're at about 5. This year we have a week, a very hot week, more than 40 degrees Celsius at the worst time for the chickpea. So the yield was reduced. The plants were kept alive and even gave 1 or 2 layers of pods later, but couldn't really go back to normal development afterwards. We can see the ability to predict yield from ground level. And if we look at each of the days after emergence, we can see this after 90 days, we can see that the root mean square error is the smallest. And also for the second season, this is the area of the smallest, so it's about 90 days after emergence, and this model is based on 2 different seasons, both of them spectral data 90 days after emergence, and to predict the yield with calibration and test and independent validation. This is what we see here. If we go back to the satellite, this is a field, the commercial field. You can see this is 400 meters. The 3 treatments in the middle, the 3 well irrigated, 100, 120, and 140. The 50% is here, the 75 is here, or 80, and the rest of the field is also 75 or 80. You can see that based on Venus, this data is from 2 fields, this field and another one. And we can see that the water potential is also linear and even with better error than was on the ground level. And the same goes for LAI. So this is what we're doing. And we decided to work on to build a model to assess. If we have the model to assess, let's draw it back on the map. And we can see that we can assess leaf water potential. LWP is leaf water potential, and these are the units. It's megapascal. And this is it. And the idea we're trying, this is in Hebrew, I'm sorry, but we are working on developing using GEE. Omer is working on it with our collaboration with the Ministry of Agriculture, working on having like an application for farmers, Israeli farmers at least to start with, to work with to know the water potential, to look at it as an additional tool, not the only tool, but an additional tool to estimate what's going on in their fields. This is it. Now we'll move for UAVs a little bit. Long time ago, it looked like that. This is southern Germany more than 100 years ago. And if you look at the picture here, you see it's blurry on the sides. And I guess that this time it was hard to synchronize between the flapping of the wings and taking the pictures. Today with UAVs, it's probably much better. And I think already in the First World War, people learn how to shoot through the propeller. So it's okay. It's time. This is in collaboration with Non Carnielli when I did my postdoc period with him in his lab in Sde Boker. And we worked with a company called Evogen. They had a nice experiment for corn. We used a UAV with 11 bands that mimics the Venus bands that we talked about. This experiment, there are 4 blue ones that are fully irrigated and 4 brown reddish ones that are deficit irrigation. In each of them, there are 90 or 20 maize cultivars. And the idea was to compare how they behave under the same cultivar in 4 replicates each with 2 irrigation treatments. And the cameras that we used in Arnon's lab was a Tetracam, 12 bands. Each lens here is related to 1 band, and the 12th one is connected to a sensor that is facing up. The same idea. Every picture taken, there is a sensor collecting sun radiation, so can be corrected and get good reflectance. This was the idea, and this was the UAV. It's the same guy. If we look just at the yield, on the x-axis, it's cultivars, genotypes. On the y-axis, it's like a ear weight, and this is grain. And we can see that some cultivars are more or less affected by the drought. This is just to show that plants are not homogeneous. And this was a sandy soil in this place, so the effect of irrigation was probably stronger than might be in heavier soils. If we look at yield predictions, this is R2 stage. In a second, we'll show that. But we see the ability to predict yield. We can see the model. It's not the best, but this is what we could do. And if we look here, we can see the development stages on the x-axis. V10, it means the plant has 10 leaves. V12, it has 12 leaves. VT is tasseling, so you have the male flowering at the top. And R2 is reproductive 2, R4 is reproductive 4, it's development stages of the ear and the grains in it. So on the y-axis on the left, we can see the R square. On the y-axis on the right, we can see the root mean square error prediction. So we are looking for small error and high R square, and the time for that was R2 stage. And the errors that we can see was not too bad. We're talking about 200 kilograms per hectare, and we see the values here are going to up to 18. So we're talking about 10 or more or less, depending which volume you are, about the error itself. Other traits that we used, that we used to estimate is one is leaf area index, and you see that it's nice. Also canopy cover, it's nice. We see here on the measured part that it's not crossing the 100, which makes sense because it was measured. But in the predicted part, some of them are higher than 100 because it's a model. Sometimes you estimate more than you actually have. So this is it. Another one is also the water content. You take the wet plant, you dry it, you wait, you dry it, you wait, and then you have the water content in it. And the idea was to see the effect of each of these traits, canopy cover, relative water content, and leaf area index on the yield, the correlation for each of them to the yield. And we can see that it's not very high. On the R2, unfortunately, we don't have the data, but we see that it's not high in other dates. So what we get, the ability to predict yield, is not coming from 1 or 2 or 3 traits. It's from the whole traits of the plants. And this is something that I think is important. But in some traits, you can go directly, or materials, you can go to specific wavelengths. The concept of the work with the maize was to take an image. If we know the development stage, run it, get the model, and estimate yield. If you don't have like ability to find if these plants are irrigated or not, and then you can get the development stage and then check it. If you want to come back in 2 weeks, go. If you want to use the right model for this development stage, use it and then predict the yield. There are many papers talking about how to analyze remote sensing data and what is the best way and what good data can be used. And using, you see UAVs and satellites, and you can see RGB and hyper and multi. And the smallest part is what you actually need for agriculture is early weeds, nutrients, pathogens, drought, early detection, yield, detection of lodging, and stuff like that. In some cases, it's a good paper, but I don't understand why multispectral for nutrients deficiencies is better than hyperspectral from UAV. And there are other points like this. So it's a good paper, but any paper that you read, try and read it in, it's not, let's say, it's not the Bible. And sometimes make sure that whatever is written makes sense for you as well. And we're working on also on phenotyping in the Whitmax project. I forgot to say that the whole chickpea project is with a few people, with David Bonfil from Gilat, and Professor Shachalabo from here, and Ran Lati from Neve Yaar, and Asaf Avneri with an agricultural guide, and Zvika Peleg, and I hope I haven't forgotten anybody. And here in the wheat, we're working on the Whitmax project. It's with Professor Zvika Peleg, Roy Ben David, people from a research station in Shechem also. And we see here an orthophoto RGB and a hyperspectral line on it. And we can see ability to estimate leaf area index also for wheat. We are using hyperspectral camera on the UAV. We can see this is a line because if it's line scanner, it scans a line and the UAV is flying and then another line and another line and another line. If it's stayed in place, it will just scan the same place, line after line. So we need to, the idea is it's calculated. You get the speed of the UAV together with the integration time, and then you can sort it out. But the UAV is sometimes moving a little bit from side to side, and therefore it looks like that. If we look at this gray panel here that we use for calibration, this is a reflectance. It looks like the sun. And if you look at vegetation here, you'll get something like that in green. After we do the correction, it looks much better. And we see that the reference line is flat it's 22% because it's gray. If it was white, it was 100%. And you see that the vegetation looks differently, just the color was switched. Instead of vegetation is green, now the vegetation is yellow, but we can leave it that. We can see in this field, we can see the covers on this side on the right. And this is our, what's mentioned here, rainout shelter is a new system that was built here in our farm in the Faculty of Agriculture. People, Professor Shukri Saranga and Vika Peleg have worked for it for many years. I'm just a little bit more than 3 years here and gave my modest contribution for that. And if we look above, this is it. And if we look from the side, we can see it over here. 1, 2, 3. And the idea is behind that, each of these covers can move all the way up to this road. And we can grow wheat, which in Israel, it's a winter crop. And in Israel, winter is wet. So we have the rains, and most people do not irrigate wheat in Israel. So they count about the rain. And you want to see how the wheat is behaving under drought. To do that, we need to cover it. So every time it's raining, these covers are automatically moving, covering the wheat. After the rain is gone, it takes off, and then the plants can grow in the same conditions, in the same soil, and the only difference is water. This is what we have, and you can see here also always that is working on a platform that takes sensors on the ground. We've just started with that project, working with some collaborators here, but always developing the integration of the systems and the cart itself, and it's doing it great. This is also about wheat work that was already done by Gabriel Mulero, measuring leaves in contact, doing indices analysis using selecting the best 2 bands combination to estimate chlorophyll contents. We have chlorophyll A, B, and total. You can see that the models are very good. We have this paper to be submitted. It's under review. It was submitted, we got revisions, we need to rearrange and submit again. So this is for the wheat so far. We are working also with some sesame. And you can do with sesame many things. It's a unique plant, not a lot of research about it, but it's becoming more and more important as people look for healthier food with iron and other advantages. In this, jumping in this guy, we can see we looked at 5 different cultivars of sesame. We can see that they are spectrally different. And we can see the places that they are different in. We use the TGI. This was work of Rom Tarshish. He did his master's with that. And we see that the TGI is an index that calculates the area between these 3 points, the triangle. And he compared it for the different days, day 32, 33, 34, 47, 48, 60, 60. We can see that these days are similar, and there are some changes that are staying for the entire year. Each color is a different cultivar, and you can see that the reflectances, the relations between the cultivars are similar throughout the season. Another experiment that Rom worked on was a cross for nitrogen and water. If we have WL, it means water limited. If we have 15, it means a low amount of nitrogen. So it's low amount of water and low amount of nitrogen, low amount of water and high amount of nitrogen, high amount of water and low nitrogen, and the control, like best conditions, is high water and high nitrogen, and C is for control. It's only 30 plots. We had, to be honest, we had 6 treatments, but we are not talking about, so we have like 6 plots and we have 5 replicates for each. We can see here the differences between each color stands for a different treatment. We can see that at day 52, if we look at the 2 bands combination index, we can see difference between, this is where irrigation started, the treatment started, the day after you see nothing, 10 days later you see some differences between the treatments. You can see that these 2 can be separated, no water, less water, less nitrogen is different than a lot of water, a lot of nitrogen, but to separate between the 2 middle ones, for now it's not possible. And for that, Rom did also some analysis for pigments, and he's done a great job like Gabriel did. In some cases, the results are even better in some of the cases. But the idea now is that if we work on leaf level by spectral means, it's hard to get the fine-tuning for separate between different stresses. But if we're going up for UAV, we might be able to do it. And on that, this is our images, the same idea as we've seen before. And who is working on that now is Maitreya. He's a visiting PhD student from India, and he's working on that and is starting to get very nice results on this study, working on the leaf level, and now we're moving for the UAV level to work with, analyze. And another thing, just to close to wrapping up, as I see my time is about to finish. This is an experiment, huge experiment with Sesame, many plots, more than 1,000. You can see each of them, and if you look carefully for closer, we can see that they are very different. The colors are different, and if we look closer, we can see that here we see 3 plots. In the middle, there are plants that are dry, ready to be harvested. On the right, they are yellow. They are very tall plants. They are yellow, so they are about to finish their life. And this is full green, so it's still flowering and growing. So in the same place, same time, 3 completely different cultivars. And as we saw with the viability in the entire field, it's huge. So relating spectral data and genetics is it's much in the front of research this day, and this is what Roy Sada is doing for his PhD. This is a Whitmax project that we mentioned. We mentioned about the last year experiment. This is what we see. And again, the combination of genotype, environment, and management, that now that we have the rain-out shelter, we can explore and to go deeper in that. After talking a lot about data and not much about how to analyze it, but just to show the possibilities, the huge possibilities for that, it's important to say that I think we need multidisciplinary teams. Like, if you get people to analyze data, you can get a result like this, which is great. You have 97% explanation. It means that fresh lemons imported to US from Mexico are negatively related to total US highway fatality rate. So it means if United States want to reduce fatality rates, it needs to import more and more lemons from Mexico. Theoretically, it will work. It's explainable for 97%. So if we find a trait like this in the plant, it can happen and people can go crazy. But for working on agriculture, agriculture, breeding, precision agriculture, urban farming, whatever, there are tons of data today, genetic data, phenotyping data, and it all must be analyzed in a good manner. And teams should have people that understand plants, soils, people that understand and know how to collect good data, how to pre-process it, how to analyze it, and how to look at the conclusion. It's not enough to have one person that will do it, and in that case, probably we'll get something like that, unless this person is very, 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 very talented. And this is a phenotyping that centers that we have, and this is how it looked like a while ago, and this is how it looks now. And if we talked a little bit about technology, it's also, remember, technology is great, but don't forget the basics. This is my suggestion, at least for myself and for others. I'll be happy to try and answer and take questions if there are any. And if people want to communicate us, they can do it via Arun or directly, whatever you prefer. And thank you.
Thank you very much, Itai, for the nice, interesting, informative session. I hope most of the people who are from a machine learning background will actually find it very interesting to apply their machine learning skills to these problems. So now let's go to the participants if they have any questions. Please, either you can raise your hand. Yeah, already I think there is one hand. Yeah, you can unmute.
Question in the chat, it says, is these tools and techniques be applicable useful for Indian farmers? Will they be affordable for them? It's a huge question about affordability. I can tell you about our lab. What we do is what we want to develop with the chickpea. It's supposed to be like a free. If you have a cellular phone, and you know how to order or write an email, you can handle with that. But other things, it's pending the companies. I don't know. It's hard to say. And what is the scope of thermal remote sensing in agriculture? It has big scope for drought and disease, but I think that, let's say, just today I talked with Professor Shuki Saranga, and he's working with TEF, and he found some phenomena with lodging, and it goes against what you expect to see. So if you look at thermal data alone, there is no way you'll be able to find it. I don't want to say exactly because he's not published it yet, but we just today talked about it. And if we use thermal data and spectral data, we'll be able to know for sure what you're getting, if it's lodging or another thing. This was something to talk with that, and I think the idea, like the thermal scope is huge, the spectral scope is huge, and the idea is to find simple solutions, because probably hyperspectral UAVs will not be practical for somebody growing a chickpea or maize in huge areas or very small areas. It takes a lot of time to operate it and to use it, and it costs money to buy it. But if we develop based on the hyperspectral data, we can develop something that is simple. This is the idea. And for commercial agriculture, in most cases, I think it will be satellites, less than UAVs. UAVs for cash crops, for, I don't know, strawberries, grapes, stuff like that, for something that is very expensive. And just to say, I think the potential for machine learning and deep learning for agriculture is huge, because you have a lot of free data that is going around. You have satellite imagery that is going around. You have weather information that is going around, and people, it's up to companies how much they charge for it. But some people are doing stuff for free.
Professor Arun sir, sorry to interrupt. Can I ask question with the professor, if you don't mind?
Sure, please go ahead.
Very good evening, Professor Herman sir. And my question is, like, my name is Manigandan. I'm working in single image de-icing. And the thing is, especially into de-icing, and even we try to get images from UAV. But I just want to know that all the images, whatever, for example, if you see in the slide that you have given in slide number 56, it's a very clear image. During haste, or else, for example, due to any pollution, whether it is possible to clear, to get the vegetation index exactly.
What we got here on the right side, this is a UAV, this is also a UAV. Both of them are just RGB, but we can get, I didn't get what exactly was your question.
So the question is, for example, in India, most of, for example, if we take North India, during winter season, the images are not very clear. Okay, even the cost. So in that case, whether it is possible to get the vegetation index exactly as determined by our predictor or not, by the satellite images also. That is
for satellite imagery, clouded area is a challenge. There are areas that are clouded for months, and it's hard to get a good image. So for that, people are going to work with radar imagery that can penetrate through the clouds. But if the atmospheric correction is not good, it's hard to account for the data. It's hard to account for it. And this is what I'm saying, that remote sensing is not perfect. If there are clouds, there are clouds.
Yeah.
And
okay. So, okay, thank you so much, Professor. Thank you so much, Professor Arun sir also.
Thank you for the question.
Any other questions, participant?
There is one in the chat, something. Okay, it's mine. It's private. Okay. Okay.
So I think if there are no questions, we'll wind up the session. And